Motion of a charged particle. Motion of a charged particle. Motion of a charged particle in a uniform magnetic field. Motion of a charged particle in a uniform magnetic field. Plus Q be a positive charge, plus Q be a charge, and this is Y and Z axis, Z and Y axis. This will be Y axis, and this is X axis. Y axis and X axis. That means plus Q charge will describe a circular orbit in XY plane. Also, the positively charged particle, that means plus Q, will be is moving with velocity v in xy plane, and we can draw the center of circular orbit in xy plane. O be the center of this circular orbit in xy plane, and a magnetic field B acts parallel to the z-axis and perpendicular to the direction of motion of the charge. And the charged particle, that means plus Q, will experience magnetic Lorentz force Fm towards the point O in xy plane or along y-axis. And this magnetic Lorentz force Fm provides necessary centripetal force Fc. Necessary centripetal force Fc for the revolution of this charged particle in clockwise direction, and r is the radius of this circular orbit described by the charged particle, and the charged particle travels clockwise in this circular orbit. Let a charged particle of charge plus Q and mass m, it should be positively charged particle of mass m, moves with a velocity v in xy plane, moves in xy plane with a velocity v, and enters in a uniform magnetic field. Enters in a uniform magnetic field of magnetic field induction B or magnetic flux density B. Enters in a uniform magnetic field of magnetic field induction B, which acts along z-axis, The magnetic Lorentz force experienced by the positively charged particle, the magnetic Lorentz force experienced by the charged particle of charge plus Q, which enters in the uniform magnetic field B, perpendicularly, that means theta equal 90 degree, is given by Fm equal QVB sin theta, where theta is the angle between the direction of motion of the charge and magnetic field induction, where theta is equal to 90 degree, which is the angle between V and B, means the direction of velocity and magnetic field induction, between the direction of velocity V of the charged particle and the direction of magnetic field induction, B. equal QVB sine 90 degree. Therefore, Fm equal QVB, only QVB, Fm equal QVB. This is the expression of magnetic Lorentz force experienced by the positively charged particle which enters with a velocity v perpendicular to the direction of magnetic field induction. This magnetic Lorentz force acts perpendicular to both v and b, which is according to Fleming's left-hand rule, and acts along y-axis from the point A such that it provides necessary centripetal force Fc. It provides necessary centripetal force Fc for the revolution of the charged particle in a circular orbit. It provides necessary centripetal force Fc for the revolution of the charged particle in a circular orbit of radius r in xy plane. Plus q be the charge in the diagram which is at the point A, and it is trying to move with velocity v in xy plane at an angle 90 degree with the direction of magnetic field B. Magnetic field B acts parallel to the z-axis, and this plus q charge experiences a magnetic Lorentz force Fm, which provides necessary centripetal force Fc, and the charged particle travels in clockwise direction in a circular orbit of radius r. R is the radius of the circular orbit, which this circular orbit exists in xy plane. Therefore, the centripetal force is equal to magnetic Lorentz force. Centripetal force required for the revolution of the charged particle in circular orbit will be equal to the magnetic Lorentz force, or Fc equal Fm, or mv square by r equal qvb. Therefore, r equal mv by qb, mv divided by qb. mv is the linear momentum of the charged particle divided by charge into magnetic field induction or magnetic flux density. So this is the radius of the circular orbit. Described by a charged particle which enters in a uniform magnetic field B perpendicularly. So plus q be the positively charged particle which is at the point A, and it travels with a velocity v in xy plane. Magnetic field B acts along z-axis such that the velocity of the charged particle is perpendicular to the magnetic field, and this charged particle will describe this circular orbit. Charged particle will revolve in a circular orbit clockwise direction, and the radius of the circular orbit will be r equal mv by qb. Hence, a charged particle enters in a uniform magnetic field perpendicularly. When a charged particle enters in a uniform magnetic field perpendicularly, the charged particle, there should be when. Hence, when a charged particle enters in a uniform magnetic field perpendicularly, the charged particle will move in a circular orbit. Hence, the charged particle will describe a circular trajectory. And the radius of this circular orbit is r equal mv by qb, where mv is the linear momentum. Divided by q into v, divided by charge into magnetic field induction or magnetic flux density. Therefore, the radius of the circular orbit, that is r equal linear momentum, means mv, divided by charge into magnetic field induction. That is the expression of radius of the circular orbit described by the charged particle. And if we compare this with the motion of the charged particle in a uniform electric field, then we can write when a charged particle enters in a uniform magnetic field perpendicularly, it will travel in a circular orbit. And when a charged particle enters in a uniform electric field perpendicularly, it will travel in a parabolic path. So if we consider uniform magnetic field, that means charged particle enters in uniform magnetic field perpendicularly, it will describe circular orbit. If the same charged particle enters in uniform electric field perpendicularly, it will describe a parabolic path.